Hi, and welcome to 10.6 potential difference, or in other words, voltage. So you've probably heard of voltage before, but maybe not heard of it in terms of potential difference. And before we start, I'm going to try to explain what potential difference means. And yeah, let's talk about it. Now, at this point in the electrostatics unit, we're getting pretty conceptual, and I like to make a comparison at this point between gravity and electrostatics. Since both are examples of field forces, there's a lot of similarities between the two concepts, and it's going to help us get a better understanding for what this term potential difference means. It actually has to do with potential energy, gravitational potential energy, and then you could have what's called electrostatic potential energy too. But a lot of times people don't talk about electrostatic potential energy, they just talk about the potential difference. So we'll talk about where that comes from. So if you imagine like this is Earth, and this is some mass within the field of Earth. The mass is going to feel a gravitational force, Fg. And that's because it's in the field. And the gravitational field of Earth looks something like this. Like this. This is just a close approximation of what the field looks like. And the stronger, the closer you get to Earth, the stronger the field is. So there is a difference in the strength of the field, and we use little g to determine the gravitational field strength. Similarly, you could have, maybe it's a metal sphere. So this is a metal sphere that has some charge Q. And you could put another charge here, and it feels an electrostatic force. Instead of Fg, force due to gravity, we call it Fe, the electrostatic force. And the interesting thing is, if this is positive and this charge is positive, it repels it. But since we drew like this, let's have it be an attractive force. And we always use a positive test charge, so let's keep that the way it is. And in order for it to be attractive, the source charge must be negative. So you have a positive and a negative. There's an attractive force there that we call the electrostatic force. And again, this electrostatic force arises because that charge is within the electric field of the source charge, which we can represent like this. And that field also, the closer you get, the stronger the field is. So there must be a way to measure the electric field strength. And instead of the little g, gravitational field strength, we use the capital E, the electric field strength. And we could write in the formulas for each of these guys. So for little g, if you look in your reference table, it's Fg divided by the mass. And this is equal to G m1, m2, meaning the mass of this plus times the mass of that, divided by r squared, the distance between the two of them we called r. And similarly, you could have the electric field strength, which is the electrostatic force divided by the charge. So you could see the similarities here. Mass is an intrinsic property of matter, just like charges. So you could think of them as similar ideas. And Coulomb's law tells us that the electrostatic force is equal to K. So instead of the gravitational field, instead of the gravitational constant, we have the electrostatic constant K. And then instead of the two masses, we have the two charges. So this is K Q1, or you could call it Q naught, because that's what we did. So instead of Q1 and Q2, we'll call it Q naught and capital Q, because we had a capital Q down here. So this is the test charge and the source charge there, divided by the square of the radius. Again, the further away you get, the weaker the force is going to be. We call that R. So that's nothing new. This was introduced in 10.4, and this was introduced in 10.5. Let's get to the new concept of potential difference. So now let's look at gravity here. In order to move this mass upward, I need to exert a force over some distance. So force times distance, that's equal to work. So the work done is equal to the change in your energy. And it's not just any type of energy. So at this position in the field here, I have some kind of gravitational potential energy. And now as I move up, I'm gaining gravitational potential energy. Where is this energy coming from? Well, I'm doing work on the system. So the amount of work you do is equal to your change in your gravitational potential energy. Similarly, you could have this attractive force here, and you would need to exert some force in order to move this upward to a new position, because these two guys are attracting each other. They want to be close together, but you're going in the opposite direction. So you need to exert a force over a distance. Again, you're doing work, and that's equaling a change in your electric potential energy. Okay, so now we have this idea of there's a similarity between gravitational potential energy and electric potential energy. And we could write a formula for the gravitational potential energy. We know it's equal to mgh. The more mass you have, the more energy you're going to have. The stronger the field is, the more energy you're going to have. And as we saw, as you increase your height, you're also increasing the amount of potential energy you have. So it's equal to mgh. Let's write an equation for the electrostatic potential energy. The mass equivalent is going to be charge. We said charge is like mass. And instead of the gravitational field strength, we're going to use the electric field strength, capital E. And technically, we could put an H here. It's just a measure of distance. But typically, we'll use a D to measure distance. So it's like just another letter for the same thing. So mgh QED. That is all well and good. We have an understanding of that because we have a basis. We already learned about that. So this kind of makes sense. We're just using the same variables. Time to introduce the new concept for today. Not potential energy, but just potential. And there's a difference in the potential. So the reason we have to introduce this is because the electrostatic potential is more of a description of the field than something that an object in the field has. So let me say it this way. The force felt by this mass is dependent on what this mass is, right? We have it in the formula here. So the more mass you have, the more force you're going to feel. The same thing with this energy. The more mass that this thing is, the more energy you're going to have. But what if there was no mass in this field? What if we were just talking about the field itself? We have a way to measure the strength of the field. We say, well, if you were to put something here, you would feel this many newtons of force for every kilogram of mass that you have there, right? So if the field strength is 9.8 newtons per kilogram, that's a force per mass, right? Newtons per kilogram. Then you're telling me that the strength of the field for every 1 kilogram of mass there, you would have 9.8 newtons. If you put 2 kilograms of mass there, in order to have the same field strength, you would feel double the force. You would have 19.6 newtons. So the gravitational field strength is just a way to measure the field without actually putting anything in it. If you do decide to put something in it, then it would feel this force. And the more mass it is, the more force you feel. And the more mass it is, the more energy you have. But let's come up with another quantity that just describes the field. So just like we're describing the field strength, well, how about if there was a way to describe the field in terms of potential? How many joules of energy would you have per kilogram of mass at that point in the field? So what we have to do is divide out this mass. So that goes away. This is some kind of term that's equal to the gravitational potential. And we said before that work is equal to the change in the potential energy. So we have W, and now we would want to divide that by the mass. So that's equal to the gravitational potential. And now this is just measuring the field itself. So it's saying for this point, for here to here, you would need to do this much work for every kilogram of mass that you put there. That's kind of what it's measuring there. So it's like the difference in the potential. So this is the potential difference. So now we have quantities that tell us the force and the energy for the particular mass that you put in the field. And we also have quantities that describe only the field itself, regardless of how much mass you put there. Let's do a similar thing for the electrostatics. So we said this was equal to the work that you're doing. And we want to get a quantity that isn't reliant on the charge in that field. So let's divide out Q from here. And now we have this electric potential. So this is, again, the potential difference. And now we have this handy formula that describes how much work you would need to do in order to move 1 coulomb of charge from one position to another. So this is the work needed per coulomb of charge. That is equal to the voltage. So that's where the term voltage comes from. It's just another way to say potential difference. They mean the same thing. Potential difference and voltage. How much work is required per coulomb of charge in order to move it from one position to another. All right, let's do some problems. So the question says, what is the total amount of work required to move a proton through a potential difference of 100 volts? So the voltage is equal to 100 volts. And they're telling you it's a proton, so that's like hidden information. They're also telling you the charge, because the charge for one proton is still 1.6 times 10 to the negative 19 coulombs. And that's important to know because our formula looks like this. And now we have enough information to determine what the work is. And so you could put the units in there. So a volt times a coulomb is equal to a joule. So the work is equal to 1.6 times 10 to the negative 17 joules. You do a lot of work, you get a lot of joules. All right, number 2, the potential difference of 10 volts. So V is equal to 10 V. Let's pause here for a second. Look at this formula. If you told your math teacher X is equal to 10X, they would be like, yeah, only when X is equal to 0, this equation makes no sense. But remember, they're not both variables, all right? They're not both X's. So this is the variable. This is the unit. It just so happens that they have the same letter. So the voltage is equal to 10 volts. That's like saying the distance is equal to 10 meters. But instead of having a separate letter, which makes it make sense, you have the same letter, which sometimes people get confused about it. So I totally understand that. All right, so it says, what is the magnitude of charge that requires 2 times 10 to the negative 2 joules of work? So the work that you're doing is 2 times 10 to the negative 2 joules. If you needed to do that much work in order to move it through a potential difference of 10 volts, how much charge were you actually moving? Was it a lot of charge or not that much charge that required this much work? So the V is equal to the W over the Q. 10 is equal to 2 times 10 to the negative 2 over Q. And be careful here. When you cross multiply it, you get 2 times 10 to the negative 2 is equal to 10Q. And then you divide like this. So I bet a lot of you guys probably flipped it. You did 10 divided by 0.02 instead. And you get a charge of 2 times 10 to the negative 3 coulombs. Or you could write it as 0.002 coulombs. But we like scientific notation. Okay, number 3. Number 3 says in an electric field, 0.9 joules of work is required to bring 0.4 coulombs of charge, 0.45 coulombs of charge from point A to point B. What is the electric potential difference or voltage between points A and B? They were nice. They put voltage here. They could have just said potential difference and you had to know what that means. And you might have looked for something like a P or a D in your reference table for an equation with that. But just remember, potential difference is the same as voltage. Okay, so you have to remember that. V is equal to W over Q. V is equal to 0.9 divided by 0.45, and you have a joule per coulomb. So instead of volts, you could call it a joule per coulomb. So you get 2 volts, or if you really wanted to, you could call it 2 joules per coulomb as well. Doesn't really matter. Same thing, they're equivalent. Number 4, 4.8 times 10 to the negative 17 joules of work is required to move an electron. So that's a key piece of information. They're telling you the charge, and they're asking for the potential difference. So you write your equation, you substitute, and you solve. So you get negative 300 volts. All right, number 5 says the diagram below shows a proton located at point A near a positively charged sphere. If 6.4 times 10 to the negative 19 joules of work is required to move the proton from point A to B, so it's a proton, what is the potential difference between A and B? And again, you have to know, okay, they're asking for the potential difference. They're really asking for the voltage. So you write your equation, substitute, and you solve. You get 4 volts. Okay. Number 6. Diagram below represents a positive test charge located near a positively charged sphere. The greatest increase in the electric potential energy of the test charge relative to the sphere would be caused by moving the charge to point A, B, C, or D. All right, so they're talking about an increase in the electric potential energy. Let me put it to you this way, right? If this was Earth and this was you, in order to increase your gravitational potential energy, you need to increase your height. All right, because you're moving against the field. So by moving against the field, you're going to increase your potential energy. Obviously, this is just for a positive test charge because against the field is relative to if you use the convention, or if you put a negative charge there, you'd have to move with the field. So, but anyway, try to visualize what's happening here, right? So we have a positive and a positive. This test charge wants to be over here, just like you want to be on the surface, all right? But in order to gain energy, you're pushing it. You ever play with magnets before? You ever have the repulsive ones? You're adding potential energy to the system. As soon as you let go of those repelling magnets, they're going to shoot away from each other. So you're storing up energy by pushing the repelling magnets together. You're storing energy in there. As soon as you let go, it's going to release that potential energy and transfer it into kinetic energy. And the same thing happens here. By moving it against the field, or by moving the positive charges closer together, you're actually increasing the potential energy of the sphere. So it'll be choice C. All right, number 7, similar question. It's almost identical, except the difference is the source charge. So it looks more like the planet Earth situation. All right, so it says the greatest increase in the electrical potential energy would happen where? Again, we have a positive test charge here, and we have a negative source charge. This positive charge is attracted to this source charge. Before, it was repelled. This was showing the different thing. All right, but it was being repelled by it, right? So now it's being attracted over here. So in order to add potential energy to the system, you'd have to move it against that force. If we put it at point A, now you're storing more energy in the system, same as if you're at Earth and you're being attracted to Earth. Well, if I increase your height above the Earth, now you have more potential energy. So it's the same thing. Basically, if you're moving against what the field is doing, or your attraction or repulsion, you're adding energy into the system. Number 8 says the diagram below shows 2 identical spheres. Sphere A has a charge of positive 12 coulombs and sphere B is neutral. After contact, the spheres separate and move apart. As the distance between the spheres is increased, the electrical potential energy of the system, what happens to it? So first, let's talk about this part. They are separated and then move apart. So the total charge here, this is 0 coulombs, so it's not even positive, it's just 0 coulombs. The total charge is 12 coulombs. The spheres come together, share that charge equally, and then separate. So now you have positive 6 coulombs on each sphere. Since they're both positive, they're repelling each other. They don't want to be close to each other. So if I bring sphere B over here, I'm adding energy into the system. If the spheres move further apart, there's going to be less energy in the system. So as the distance between the spheres increases, as it goes this way, the energy decreases. Okay, let's do number 9. It says base your answers to questions 10 and 11 on the diagram. A, B, and C are reference points. If an electron, so now we're talking about an electron, moves from point A to point B, the electron's potential energy will, well, it doesn't change at all. It's going to remain the same because you're still the same distance away from this positive plate and this negative plate, right? So if the electron were to go to point C, which is what the next question is, it says if an electron moves from point A to point C, so now the electron is right here, and it went this way. All right, the electric potential energy, what's going to happen to it? This negative electron does not want to be near this negative plate. All right, so you're doing work on the system. You have to exert a force over a distance in order to get it to go closer over here. So if you're doing work on the system, you're adding electric potential energy into the system. That's a different way to explain it. So that could be applied to 6 through 8 as well. Anytime you have to exert a force over a distance, you're adding energy into the system. I didn't need to exert a force against this electric field in order to go from A to B because I'm not changing the distance between the plates. But if I try to bring it closer to this negative plate that is repelling it, you better believe I have to exert a force. Or even let's look at the positive plate. This electron is attracted to the positive plate. It wants to go in this direction, but I'm bringing it to point C. I'm moving it against that, that force, so I need to exert a force this way in order to get it to point C. So it's going to increase. Number 11, which electrical unit is equivalent to 1 joule? And then they give you a bunch of options. So these type of questions come up and they could ask about any of the units that we talked about all year. So you could see any type of question like this. It's not a guessing game. You want to look in your reference table and find the equations that these units represent. So for a joule, that's work. For volts, that's a volts. This is the distance or the height. This is force. This is volts. This is a volt. This is Q for charge. And this is volts. So we're looking for an equation that relates these variables. And if the math is the same, so this is saying a volt per voltage divided by distance. This is saying force times voltage. This is saying a volt per charge. This is saying a charge times a volt. Which one of these things is equal to work? So it's just saying, do you know your formulas? So you look in your reference table for something that looks similar to one of these guys, and you have this formula here. Work is equal to the voltage divided by the charge. It's a volt per coulomb. Oh, hold on a second. No, I knew that didn't look right. So the equation is voltage is equal to work divided by charge, right? And they're asking for the joule. So let's solve for work. You cross multiply. Work is equal to voltage times charge. So this is and just as equivalent equation. If you're looking for the work, you could solve like that, do the voltage times the charge. So now we want to find the one that is a volt times a charge, or a coulomb times a volt. and that's going to be this equation here. So I could see why some people, I almost said that it was C2. That would have been way wrong, because this equation is not equivalent to this equation. They look similar, but this is saying something different. See how this is different from that? Work doesn't equal volt divided by charge. It's equal to the voltage times the charge. So this is no good. We want choice D. That's not it. This is it. Okay, pretty tricky, pretty tricky. It's all about finding the relationship. All right. Last question. Says the graph below shows the relationship between the work done on a charged body in an electric field and the net charge on the body. What does the slope of the graph represent? We've done a bunch of graph questions in the beginning of the year with mechanics, and we said, okay, slope is equal to the rise over the run, change in y over change in x. Then you ask yourself, what are the y values? Well, in this case, it's the work. What are the x values? In this case, it's the charge, which we use a Q. So you look in your reference table, which physical quantity is equal to work divided by charge? That's going to be voltage. Oh man, voltage isn't over here. Don't forget, potential difference is another word for voltage. All right, that's about it. Have a good day.